For today's episode, we will cover autism and eye movements. The eyes are the most underrated, unrecognized part of our biology. And the retina is my number one, my favorite brain region. So much of human life involves vision. And the eyes, which includes non-image forming structures of our biology, of our life. In addition, so much of the brain is dedicated to vision. When we add the non-image biology of the eyes, that adds more and more brain real estate, brain structures. To note, blind people still use their eyes for these so-called non-image forming biology, for our physiology, for our life. Life happens through the eyes. Even blind people use their eyes for the non-image structures. The easy one, and likely most important, is melanopsin, monosynaptic to the suprachiasmatic nucleus of the hypothalamus, the SCN. We've covered the SCN. This is the master clock. And there is a reason that master clock is in the eye, sharing structures used for vision. By the end of this episode, you might learn about the roles of our eyes in a way not previously considered. If you have considered these roles, you might learn some more specific connections to the autistic phenotype. We will add in some information about the eyes and oxytocin. And think about visual processing and seeing details to general. Meaning, autistics see the details in our vision to the larger object. This is in real time as we navigate the world and in controlled settings, when autistics see a specific detail within the larger picture. And think about pattern thinking, an ability to see patterns. We are similar to AI. Think about the cranium nerves, especially the sixth, the abducens, the precision of our two eyes, and how these are complete, separate structures, completely independent from each other. The eyes are incredible. Life happens through the eyes. With autism, it is easy to see. With eyes, of course, some odd characteristics with the eyes, such as eye contact. But what does this mean? It is easy to attach the lack of social skills, social cues, ability to socialize. And we know criteria A, the social communication and interaction, A1, A2, and A3. Those are easy. Remember the episode on eye tracking? And at 14 months, eye tracking serves as a reliable tool for diagnosing autism with significant validity. This is in addition to the normal assessment tools. If you add in eye tracking, at 14 months, adding in the eye tracking to the normal autism assessment instruments has vast improvements. Besides the social aspects, today we will explore some biological components that underlie autism and eye movements. We will expand on a popular brain region of the podcast and in autism research, the dACC, anterior cingulate cortex, and zoom into the dACC with a specific subdivision, the dorsal anterior cingulate cortex. Remember how fascinating the cingulate is. And it wraps around white matter tracks. Today, we will discuss a very interesting region, the superior colliculus. This is a very powerful region. And as a brief introduction, the superior colliculus integrates sensory information. The easy one is, if you hear a noise to the right, your head and vision turns to the right. Your eyes pick up where that noise came from. This happens nearly every time. Probably more accurate, this does happen every time. This is a powerful reflex. It is a machine-like response. The superior colliculus biases our attention based on those sensory inputs, that sensory information, in large part for what is salient in the environment. Here, we can think of the reason it has so much power, and it biases us using reflexes. It detects threat. Remember a goal, or the goal, meaning the number one goal of the central nervous system, is to move the living organism. Yet another goal is shifting learning into habits and conserve habits by shifting those into reflexes. It saves energy and is optimal for survival. The superior colliculus is known as a first responder. It is located on the upper area of the brainstem. Remember the substantia nigra from the basal ganglia episodes. And remember the locus coeruleus from brain adrenaline, the little nuclei for norepinephrine, and especially that internal calculator we covered involving astrocytes when measuring effort versus outcome, or persist or quit. This midbrain region is just below the thalamus, our primary sensory relay station. Already, you should be picking up on why this is a region of interest for the autistic phenotype. However, I am going to take it to a place that autism research hasn't explored. Autism is in the womb before the central nervous system is created. The neural tube is its precursor in the little embryo. Remember some discussion on neural ectoderm. The neural tube goes into 4 subdivisions to create the central nervous system. The only one that remains is the area we are talking about, the midbrain, also called the mesencephalon. This stays as is. This is remarkable because of the connections with motor movements and sensory processing, and so many coexisting conditions with the body. The superior colliculus has significant roles with how we bias and send our attention. Think about it. How often do you consciously think about where to look versus how the machine and these reflexes handles that for you? This is why eye gaze, our vision and breathing, is very fascinating. Mostly, these are under unconscious control. However, we can take control of both. And both eye gaze and breathing, both depth and rate of breath, are in direct bidirectional connections to our autonomic nervous system. And that is powerful, meaning what we are looking at can influence the levels of stress and calmness. And how we are breathing can influence our stress and calmness. Bidirectional. It can make us stressed or calm, aroused or calm. And stress and calmness can change our eye gaze and depth and rates of breath. The more stressed you are, the narrower your vision. In other words, the more focal or tunnel vision you have. The peripheral vision is gone. This is the threat detection machine. This was a long sidebar, but relevant. Relevant because this is operating outside of deliberate control. In autism, that eye contact and salience to the environment is limited, but for good reason. Remember, this is huge takeaway, and I want the listener to know. The biology that gives us autism allows us to be comfortable within ourselves. This should all be making more and more sense. So the superior colliculus integrates visual, auditory, and somatosensory information. That attention bias that acts on those reflexive functions of the brainstem. So eye gaze. You might see or hear about saccadic eye movements, which explains quick eye movements to pick up targets in the environment. How we orient to the world or to the environment. What is even more fascinating and crucial, the superior colliculus shapes brain development. If you think about upstream connections that dictate downstream connections, and thus strengthen of axons, strengthening what is preferred in our circuitry, the source of learning opportunities. All of these items are sources for the maturing brain. These sources mature the brain. Learning from an early age, learning the environment, learning what is salient, and how to navigate the environment. Think about where the 3-month-old or the 6-month-old or the 18 to 24-month-old infant or baby or developing organism, whatever verbiage you want to use there. Think about where they're sending their attention. Based off of this data we are covering. And think about how these symptoms manifest, the personality and the traits manifest for the autistic phenotype. Interestingly, and we have covered many times the altered salience network in autism. And the study from UCLA showing this at 6 weeks old. Vision is huge for the living organism. Another fascinating connection are saccadic eye movements in schizophrenia are similar to autism. Sensory organization, learning, navigating the environment, developing of the brain and the central nervous system, and conducting motor movements, indirectly at minimum. All of this sounds like autism. Think about our senses. And a couple of things here. Let's cover afferents, or inputs, and efferents, outputs, of the superior colliculus. So inputs and outputs. Afferents, or the inputs, some obvious ones. The retina, visual cortex, which is sending visual details that ultimately influence where and how attention is biased and how to orient to the environment. Frontal eye fields. Okay? The frontal eye fields are organized to control eye movements. This area is mostly at the top of the head. The top middle of our cortex is a lot of motor control, and the frontal eye fields begin this area. Anterior motor cortex, to be exact. This area has tremendous roles in things we already mentioned. Eye movements, the saccadics, and attention and gaze, which makes sense. Our eyes determine where we will likely send our attention, regardless of the signal or noise. This is mostly volunteering movements. Okay, efferents, the outputs from the frontal eye fields include feedback to the superior colliculus. This sends projections, of course, to the thalamus and two subdivisions of the thalamus. The primary visual subdivision of the thalamus is pulvinar, which assists with attentional shifts and spatial locations. The second thalamus area is medial dorsal nucleus, which involves recruiting higher order functions for attention and vision. This area will feed back up to the cortex. Another area of the brainstem is a cool area called reticular formation. This is the pons and the half football shaped area on the front of the brainstem. We can absolutely parse out different reticular formations within the brainstem. We will not do that at this time. Ultimately, an area, if interested, is the so-called reticular activating system. Other areas include the parietal lobe and a frequent discussion area, the basal ganglia, specifically the dorsal striatum. Because you know by now, the dorsal striatum is the input area, the part receiving projections from the outside regions for the basal ganglia. And sensory processing is rarely singular, especially for typical developed, not just autistics. Sensory integration provides more data points for our brain. It enjoys multiple sensory inputs. Remember the thalamus and how much work our thalamus does. And the thalamus's personal assistant, covered in the basal ganglia, the subthalamic nucleus. The thalamus has a team working on what and how and when we are going to integrate our sensations and where and how to respond. Think about sensation perception and how different people are. How much different we are navigating the environments. Think about how autism's criteria, social communication and interaction, and the restricted, repetitive behaviors. The thalamus underlies these. Remember in the Autism and Adaptive Responses episode, we covered the medial prefrontal cortex, including an area called the anterior cingulate cortex. In that episode, when the living organism is navigating the world, keeping up, making great choices, responding to environmental stimuli in a way that is optimal for that living organism, the medial prefrontal cortex and ACC lead the way. that so-called top-down control. Those areas control the more emotional subcortical regions. Remember an area called the ventral medial prefrontal cortex. In rodents, in scientific literature, studying rodents, studying these circuitries on rodents, this is called the infralimbic. These areas are, generally speaking, a toggle switch for action selection. Now, I want to be careful on labeling that a toggle switch, but it is absolutely equipping the living organism with certain tools, certain skills used to navigate the environment. So, if you followed along with the basal ganglia episodes, these areas are dictating or orchestrating or conducting our actions. Remember, you don't define motivations when we discuss action selections or movements. Our nervous system and neuroplasticity defines motivation. The very first step in this is sensory processing and understanding eyes and eye movements. What data are extracting from the environment? And what does that mean to us at that time? With that so-called leading the way, the ACC has powerful inputs on error detection and conflict monitoring and effort evaluation. So before we continue, you can piece together the astrocyte and norepinephrine and that internal calculator in this equation. Conflict monitoring. In autism, you know the outside world is chaotic. It is hard to keep up with, and it causes avoidance. Now, I want to connect another previous episode, the roles of oxytocin, or more specifically, the synthesis of this oxytocin from magnocellular and parvocellular paths. Think about those two distinct pathways and what the differences are for oxytocin. Magnocellular oxytocin is responsible for parental bonding, affective, or sometimes called emotional empathy, and buffering, meaning reducing the impact of something stressful. So the physiology here, see autism and anxiety as we parse that out. Autism and anxiety episode. And also psychological impact. Essentially, buffering here is the sensation perception role. Magnocellular is both central and peripheral nervous system, with roles in motion and gaze direction. Parvocellular is used for fine details and more emotional regulation. Parvocellular, which is all central nervous system, at small amounts. Parvocellular supports social reward, social cognition, and more peer-to-peer bonding, or pair bonding. Remember, when socialness is rewarding, it requires oxytocin and serotonin to converge, and the nucleus accumbens. Why this is crucial in this episode is simple. Data coming in from the eyes determines this. The eyes, as our largest source of sensations, allows the living organism to navigate the world. If the main goal of the central nervous system is to move, the living organism. The eyes seem important for this task. Oxytocin connected to the eyes in the lateral geniculate nucleus, which is the thalamus. This is where it picks up the magnocellular and parvocellular functions. This is easy to understand, but now think about the roles in autism. Both from our biology and from experience, the neuroplasticity. These areas are known as our so-called decision makers. Okay, so there you go. They define motivation. Here's an example of why and how we don't define motivation like you might if it was in so-called self-help or self-care or biasing yourself into action or learning to do X, Y, Z. You set a goal and now you're motivated to accomplish that goal. That is not motivation from the sense of the central nervous system. I didn't say that you cannot do it. I did not say that you cannot determine your motivation or you cannot change. I know we can change, and I know it takes work. With autism, there are so many things keeping us in contrast to the social norms. This whole time we have been talking about sensory processing and biasing our attention. Society says we must look at you. The biology that gives us autism says it is not that simple. And think about how much predicting we are doing. We are constantly predicting. All people do this. Think about what is moving the most from other people or on other people. One person or within a group of people. The eyes move the most. Imagine a month old or a 2-year-old or whatever age, especially around the critical period. How much innate learning is happening? If you are listening to the episode or listening to the podcast, please leave a review or rating. In podcasting, reviews, ratings, and downloads are huge, and I very much appreciate your feedback. You can contact me on X at RPS47586, and I love your conversations. Any conversation about autism that you want to dive into. You can check out the Hop link for links to all of the shows across different platforms of podcasting. You can contact me in email info.fromthespectrum@gmail.com. And thank you for listening to From the Spectrum podcast.